Lecture 3B, Model of the Seasons. What we're going to do is take those 6 factors that create the seasons and put them into a model of interaction. Now this model is based on the Earth's revolution around the Sun, and we're going to stop the Earth at 4 critical positions during the year. The first day of winter, first day of spring, first day of summer, and first day of fall. Now the first thing that we want to make note of is that these seasons occur exactly every 3 months from one another. Every 3 months on or about the 21st, 22nd, or 23rd. Now, when I'm going over the 4 seasons, I'm just going to use the 21st. I'm going to say on or about the 21st, just to kind of keep it easier so you don't have to memorize whether it's the 22nd or 23rd. And we're going to start with the first day of winter, and we're going to make note of the tilt of the Earth's polar axis, and then we're going to look at the relationship of that to the circle of illumination. So let's begin here with an enlarged diagram of the December or winter solstice. All right, it's called the winter solstice. For us in the northern hemisphere, we're experiencing winter, all right, but it can also be called the December solstice. The word solstice comes from the Latin sol, meaning sun, stis, status. So we want to look at the status of the sun's rays on this day striking the earth on or about December 21. All right, now, the first thing we want to make note of, in its orbit around the sun on this day, the northern hemisphere is tipped away from the sun. And so here we've got the Earth's polar axis, all right, tilted 23.5 degrees, but the northern hemisphere is tipped away from the sun. And we're going to be experiencing winter. This is the first day of winter for us in the northern hemisphere. Now, another thing that I want to make note of is in the southern hemisphere, the seasons are always reversed. Now, in the southern hemisphere, they're experiencing the first day of summer. The first day of summer. Now, it should make sense that since the southern hemisphere is tipped towards the sun, the most direct rays of the sun would be striking in the southern hemisphere. And as a matter of fact, right, the most intense vertical rays striking the Earth at noon, the subsolar point, is striking in the southern hemisphere. Now, specifically, what marks this date is when the subsolar point, in its migration between the tropics, has made its way as far south into the southern hemisphere as it can possibly go. And on this day, the subsolar point makes its way to 23.5 degrees south latitude. And it's a special line of latitude. We call it a sun behavior line, and we name them. And so this line of latitude is called the Tropic of Capricorn. Now, where have we seen this number before, 23.5? That is the tilt of the Earth's polar axis. Right, and so it's no, it's not a coincidence. It's specifically due to the Earth's tilt of the Earth's polar axis. If the tilt of the Earth's polar axis was, say, 30 degrees, that's where the tropics would be. All right, and so this is the way the Earth is presenting itself to the sun. So the southern hemisphere is experiencing summer for 2 reasons. Well, the first reason is because it's receiving the highest sun angles, vertical rays, and then still pretty high sun angles. So if you're getting high sun angles, you're getting more direct rays of the sun and more heating, creating summer-like temperatures. Now, the northern hemisphere is experiencing winter, all right, now because the subsolar point is in another hemisphere, and as we move away from the subsolar point, the rays of the sun at noon are lower and lower and lower in the sky, and we wind up with less heating when we have lower sun angles. Now, the second part is the amount of daylight besides sun angle. And what we want to do now is take a look at really high latitude locations and what's going on with day and night. And here's another sun behavior line. It's not illustrated here. The name is not shown, but it will be in another diagram. It's called the Arctic Circle. It's at 66.5 degrees north latitude. And what we've got to do now is take a look at the circle of illumination, right, which cannot always match up with the tilt of the Earth's polar axis. Now you've got to imagine the Earth rotating. The Earth is rotating, and you can see that all locations north of the Arctic Circle are rotating through night. right? Rotating through night. And this usually happens for many, many weeks, 4, 5, 6, 7 weeks. It depends exactly where you are. And it's constant night for numerous weeks. And there are actually, towns and cities located near and above the Arctic Circle, in Alaska, northern Canada, northern Europe, the Scandinavian Peninsula. Actually, the largest city above the Arctic Circle, Murmansk in Russia, has a population of 1 million people that have to deal with no daylight for about 6 weeks during the year. And you can imagine no daylight, there's no heating, how cold it is, and how difficult it is on daily life. Now, even you don't have to be that high of a latitude. Here they're showing 40 degrees north latitude right here. That's the latitude of New York City, and also southern Europe here. But again, you can kind of take a look at the proportion of day, right, versus night. And so during winter time, in the when we're having northern hemisphere winter, we've got relatively short periods of day and longer periods of night. All right. And I remember being way up here in Aberdeen, Scotland during Christmas break one year. And look at this, very, very short period of day. I think it was only about 4 or 5 hours of day. I remember the sunrise, sun was finally out by about 10 in the morning. By 2:30, right, the sun was set. So, with 4 or 5 hours of daylight, and then what do you've got? 19 or 20 hours of night. So when you've got shorter periods of daylight, you've got, less potential sun's rays and less heating. And so low sun angles and short periods of daylight make winter. Let's look at the opposite in the southern hemisphere. Let's look at the Antarctic Circle, 66½ degrees south latitude. Now, since the southern hemisphere is tipped towards the sun, we've got another sun behavior line based on the fact when the Earth is rotating, it's rotating through the day portion of Earth. And again, this lasts for 4, 5, 6, 7 weeks in Antarctica. And now the thing is, the sun is out for 24 hours a day for many weeks. But you're not going to get much heating, right? You're not going to get much heating. What you wind up with is very low sun angles, maybe just above the horizon, because you're at the bottom of the Earth. And so even though the subsolar point is in that hemisphere, sun angles are still really quite low as you're moving, at the bottom of the Earth at the South Pole. So really what happens for, 6 weeks is the sun is just above the horizon and appears to just rotate around the horizon, all right, day after day after day, and it doesn't set. It doesn't set. Now, the thing is that the sun appears to be rotating around the horizon, but who is really rotating? Okay, it's the Earth rotating in relation to the sun. And again, you can take a look at the periods of day length versus nighttime. And so this is the second factor that's creating summer warm temperatures in the southern hemisphere, long periods of daylight. I mean, you can even, here's Australia way over here. And you just think about it, it's December and it's summer in the southern hemisphere. Christmas time, right? In Australia, Sydney, Australia is located right here at about 30 degrees. And it's in the 90s, very, very hot in summer in Sydney. And it is Christmas time. They usually go to the beach. Also, oh my goodness, December, this is when scientists go to Antarctica because, it's summer and you've got daylight. You've got daylight there. All right. Here's a kind of a nice picture of a very, very high latitude location in winter time. And when you're really far away from the subsolar point, you're going to have very, very low sun angles. So here is the sun at noon, at its zenith, right? And so you're not going to get much heating out of that. Let's move the Earth in its orbit now. Right, during the months of winter, and it's 3 months. So we're going to finish off December, January, February, and March. And what is going to happen during these 3 months of winter time, the way the Earth is presenting itself to the sun with that constant tilt angle, it's going to cause the subsolar point to actually move or migrate day by day. And during the 3 months of winter, the subsolar point is going to move from 23.5 degrees south latitude northward. And on the day the subsolar point moves northward and reaches the equator, marks the first day of spring. Right. It's called the equinox, March equinox, vernal equinox, spring equinox. So let's take a look at the details of this diagram, the first day of spring. Now technically vernal is Latin meaning youthful or spring. Equinox, and it occurs on or about March 21. So this is going to be the first day of spring for us in the northern hemisphere. Now, seasons are reversed. It was just summertime in the previous diagram in the southern hemisphere, so now it's going to be fall. Now, the important thing here, what you need to know, is the subsolar point has migrated during the months of winter time for us in the northern hemisphere and have reached the equator. And so here we're showing the subsolar point at the equator, and the sun at noon is making a 90-degree angle here. Now, the other important thing about equinox conditions is that all places on Earth are experiencing 12 hours of day and 12 hours of night. All places on Earth. And as a matter of fact, I mean, the word equinox comes from the Latin equa meaning equal, nox meaning night. And so all the inequities that we had just seen 3 months previously are eliminated. Now, in this diagram, they've eliminated the tilt of the Earth's polar axis to show you how everything is receiving equal amounts of day and night. But of course, the tilt of the Earth's polar axis is still there. It's just a different view. So I've taken a cutout from our model to show you that the tilt of the Earth's polar axis is indeed still there. Just the diagram is based on a side view. And you can actually see here the circle of illumination now is actually cutting right through the North Pole, and areas now above the Arctic Circle are experiencing 12 hours of day and 12 hours of night, just like all other places. So let's kind of just talk about that day and night at very, very high latitude locations. So remember, above the Arctic Circle 3 months ago, it was total night. Let's say after about 6 weeks, the sun came out for about 10 minutes and then set. And then the next day it came out for a half hour and set. And then the next day an hour and set, and 2 hours, and 3 hours, and 4 hours. And by the time you've moved through 3 months, the sun is now out for 12 hours. And the same is true for areas beyond the Antarctic Circle. One day, after about 6 or so weeks, the sun set for a short period of time, and then continued to set longer and longer and longer until 3 months' time, the sun has now set for 12 hours. And it's because everything is equal, right? We've got, everything in equality. And so and just imagine rotation. Now, let's move the Earth in its orbit during the months of spring. And so we're going to finish off March, April, May, and into June. And so on or about June 21, we've got the first day of summer for us in the northern hemisphere. And now note that the northern hemisphere is now tilted towards the sun in its opposite orbit from where we began. And so we're going to have another solstice situation, but everything is going to be opposite from where we began. So let's take a look at this situation. All right. It's called the summer solstice. Right? It occurs on or about June 21, and we call it the summer solstice because the northern hemisphere is experiencing the first day of summer. And now the northern hemisphere is tipped to the sun. Now, what had been going on during those 3 months of spring? The way the Earth has been presenting itself to the sun with that constant tilt angle is causing the subsolar point to continue to migrate. And what it had been doing, it migrated from its spring location at the equator, and during those 3 months of spring, day by day migrated northward. Right. And so obviously now the southern hemisphere is experiencing winter time since it's tilted away. Now, what I was just getting at is the subsolar point is now at its farthest northern location that it can possibly go. And the day is marked when the subsolar point reaches 23.5 degrees north latitude. And it's a special line of latitude, so it's named. It's a sun behavior line, and we call it the Tropic of Cancer. Again, we're going to look at the proportion of day and night. So the Northern Hemisphere is experiencing long periods of day. Take a look at, the latitude of New York City. Really long periods of day, short periods of night. And so you've got long periods of daytime, so you've got, greater chance of heating if the sun is out, and you've got high sun angles because the subsolar point is in this hemisphere. Now, the Arctic Circle is experiencing now 24 hours of daylight, so then you add the rotation, and it's just incredible. Every 6 months, the difference in the amount of daylight and darkness. And so after the spring equinox, the sun just continued to stay out longer and longer. Do you remember it was 12 hours of daylight? Well, the sun just kept on staying out longer and longer and longer over those next 3 months until we reach this situation. And the same is true for the Antarctic Circle. Now they're experiencing 24 hours of darkness as kind of rotating through the night part of the Earth. And again, since the vernal equinox, the sun just kept on setting longer and longer and longer. It was 12 hours of night, then 13, 14, 15. So at very, very high latitude locations, you wind up with huge inequities in the amount of day and night during the seasons. Now, if you're at the equator, you're always experiencing about 12 hours of day, 12 hours of night, and even in the tropics, the amount of day and night, it doesn't vary that much. But when you get to high latitude locations, like 40 degrees north, you've got, huge differences. Now, remember when I was at Aberdeen, Scotland, in December, just having about, 4 or 5 hours of daylight? Now, 6 months later, in summertime, they're experiencing about 16 hours. Right? So look at this. Look at the amount of daylight versus the amount of darkness. And so, the sun, I remember even, my goodness gracious, in Paris, if you've ever go to, Western Europe in summertime, sun rises about 5 in the morning, and the sun really doesn't set until about 10:30 or 11 at night. And so you've got long periods of daytime heating, making summertime conditions. All right, now, let's see. Let's go on to the 3 months of summertime, and June, July, August, and September. And again, the way the Earth is presenting itself to the sun is going to cause the subsolar point to appear to migrate, as the way that the Earth is presenting itself to the sun. And so what's going to happen now during these 3 months of summer, the subsolar point is now going to start to migrate southward back to the equator. And on the day the subsolar point reaches the equator on or about September 23rd marks another critical date. It's another equinox situation. And for us in the Northern Hemisphere, it's the first day of fall. And the thing that's going to be easy about this is it's the exact same situation as the first day of spring. All right, it's called the autumnal equinox, right? The first day of fall for us in the Northern Hemisphere. And then, of course, it's the opposite. It's the first day of spring in the Southern Hemisphere. And the subsolar point on this day has made its way back to the equator, and everything now is back to 12 hours of day and 12 hours of night. And the situation is the same. We're just kind of looking at the side view. Now, what we're going to do now is just kind of finish off the 3 months of fall, all right, and go back to where we began. So during these 3 months of fall, the subsolar point is moving from its equatorial location now back into the Southern Hemisphere, day by day by day. And on the day it reaches as far south as it can go, 23.5 degrees south latitude, marks the first day of wintertime. And so that's our model of the seasons. I just do want to make note of where we are today, in late January, in the Earth's orbit around the sun. Here we are here. We're about a month after the first day of winter. We still have 2 more months to go until we have the first day of spring. And what's happening during these 3 months of winter time is we're gaining 2 hours of daylight, 2 hours more heating. Now here in Thibodeau, at about 30 degrees north latitude, on the first day of winter, we have about 10 hours of daylight. And by the time we get to the first day of spring, how much daylight are we going to have? 12 hours. And so 2 hours more daylight, 2 hours more heating. And as a matter of fact, over the additional 3 months of spring, until we get to the first day of summer, we're going to gain another 2 hours, and we'll have 14 hours of daylight. Besides the high sun angles and long periods of daytime, that makes, the hot season for us. And so we keep on gaining and losing 2 hours, every season. Gaining, losing, losing. All right, this is, so we finished up that model. What I want to do is take a look at this graph showing the migration of the subsolar point during the year between the tropics. And this is where we began, the first day of winter, and here we are in the southern hemisphere. Now, these are latitude locations, and the minus just means southern hemisphere. And so we started in December, the first day of winter. And then here we are now in January. And I've got an arrow here showing where we are at the end of January. And so you can actually, see from this diagram where the subsolar point is today, or at least at the end of January, and where it's heading. So we can say basically the subsolar point is at about 20 degrees south latitude, and it's getting closer to us now. So over the next week or so, until it's February, the subsolar point is now going to move from the 20 to maybe 19, 18, 17, and then continue on. And so it's getting closer to us until in another 2 months. We're going to have the subsolar point getting closer to us. It's at the equator. And so, by March it's starting to warm up. Well, the subsolar point is getting closer to us, and we're going to have higher sun angles. And also, the day length has increased 2 hours. And then during the months of spring, the subsolar point now is moving into the northern hemisphere, getting closer to us. And we know, by April and May and, oh my goodness, June, how hot it is, all right? And so, it's because we're getting really high sun angles here in Thibodaux. And so, now remember, we're at 30 degrees north latitude. We're just, off of this diagram. And so, this is kind of a stupid, obvious question, but, does the subsolar point ever make it to us here in Louisiana? No. But it gets pretty close. On, June 21, we're just off, by what about, 6.5 degrees from the vertical, right? And so our sun angle is very, very high. It's not 90 degrees. But you just subtract 6.5, and you wind up with a sun angle of 83.5, right? And that's a really high sun angle, 83, around 8.5, 84, something like that. And so we've got long periods of daylight, 14 hours, really high sun angles, and that's going to mark our hot season. And then, of course, during the months of summer, the subsolar point is moving away from us, and this is when things will start to cool off a little bit as the sun angles are getting lower, farther away from us. And we've got the first day of fall, and then, of course, then after the first day of fall, the subsolar point is moving into the southern hemisphere. And by October, things are starting to cool off because our sun angles are getting lower as the subsolar point is farther away from us. All right, let's make a conclusion. There are really two things that create the seasons, and seasons, just think of heating, hot and cold. And what I've tried to illustrate, I've definitely tried to illustrate, is sun angle. Is definitely a huge factor creating hot and cold in seasons. And what they've got in this diagram is a flashlight. You can do this. Take a flashlight in a dark room and just have the flashlight, vertical, directly striking the ground. And it's going to mimic the subsolar point, making a 90-degree angle with the ground. And what's going to wind up happening, you're going to have, 1 unit of the sun's rays, or the flashlight rays, striking 1 unit of the ground. And so you're going to have a small but really intense bright spot. And so that's going to have you're going to get the full and intense heating, reflected by that intensity of brightness. And then let's just kind of move to a high latitude location, say in winter time, where the subsolar point is really far away and the sun at noon is making only a low sun angle. Here we've got about a 30-degree angle. And what's going to happen, do this with your flashlight. And so you've got, 1 unit of the flashlight rays or the sun's rays. But now because it's tilted, those rays are now going to be spread over twice the area and the intensity is lessened. And so you'll note that flashlight is now going to be dimmer, all right? The light is going to be dimmer over a much broader area. And so we wind up with 1 unit of flashlight rays spread over 2 units of surface area. And so you're going to have lessened intensity and less heating. Now, the other thing that we were talking about that definitely determines the seasons is the amount of daylight. And what we've seen, during the year is that it can range from, no daylight, so no heating, and it's going to definitely be winter, to 24 hours, and that'll be summer. And so, yeah. Now, yeah, so the longer, obviously, you've got daylight, and here we've got the summertime picture here. So the longer periods of daylight, the more heating, and it's going to be summertime. Now, and then, of course, shorter day lengths, here we are, where it's wintertime. You're going to have, less potential heating with the sun out at a shorter period of time. Now, these are great extremes seasonally, as you move out of the tropics. If you're at the equator, you're always, take a look at all the diagrams. The equator is always having about 12 hours of day and 12 hours of night. And the difference in the amount of daylight within the tropics, is just maybe a couple of hours seasonally, 1 or 2 hours maybe. But by the time you get at higher latitudes out of the tropics, that's when you notice the really big difference in seasonality of the amount of day and night. All right, you really big differences. So just kind of take a look at the June solstice versus the December solstice, and just follow along that 40-degree north line at the latitude of New York City, and you'll see huge differences in the amount of daylight during summer and then the amount of daylight during winter time. And here's kind of conclusion number 2. This is pretty much what we're talking about, is the sun at noon. The sun at noon. And so we've got the sun rising in the morning, reaching its zenith at noon, and then the sun setting. I've got to ask you kind of a stupid question. Is the subsolar point illustrated in this diagram? No. If the subsolar point was illustrated here, the sun at noon would be directly over this guy's head. And so this is kind of a nice diagram, actually illustrating maybe a mid-latitude location, like us here, maybe 30 degrees or 35, 40 degrees, like the latitude of New York City. And so, in summertime, we're going to have high sun angles. And for us, I think I already mentioned that, we're going to have a sun angle, pretty high sun angle on the first day of summer, somewhere around about 84 degrees above the horizon for us. And then in wintertime, we're going to have low sun angles, kind of what we're having now. And actually, on the first day of winter, our sun angle here, in Thibodaux, 30 degrees north latitude, is about 37 degrees above the horizon. So that's much lower for us. And so that's kind of what we're talking about, the sun at noon and the sun angle creating heating. All right, the final thing that we want to make sure that you know in our what you need to know for the exam is you absolutely need to know your sun behavior lines. And here they are, all illustrated here. Now, the other thing that you need to know is their degrees of latitude. 0, 23.5 degrees, and 66.5 degrees. And so what day of the year is it illustrated in this diagram? Well, it's the first day of summer. Right. The vertical ray is referring to the subsolar point. So besides needing to know where the subsolar point is on our 4 critical days, you also need to have some idea as to the amount of daylight and darkness and what's going on seasonally, at the Arctic and Antarctic Circle. And it really should make sense. If it's summertime, we're tilted towards the sun and we're having long periods of day and 24 hours of daylight above the Arctic Circle. So really, if you just think about it, it really kind of makes sense. And here's our final diagram. You know, what day of the year is it here? Well, it's one of the equinoxes. Here the vertical ray is representing the subsolar point. And so, yeah, so make sure you know your sun behavior lines and the numbers of the degrees of latitude. End lecture.